So the polynomial in problem number 14, if you look at the graph, it doesn't cross the x-axis. So, all right, that's kind of a bummer. But what that tells us is that the solutions, therefore, must all be imaginary. Because from our handout the other day, we know that for a polynomial of degree n, there should be n zeros, exactly n zeros. Now, some of those could be repeated, that's okay, but there should be n zeros. Now, because none of these, because this parabola, because this polynomial doesn't cross the x-axis in any real place, they must be complex zeros. So let's see if we can't find those solutions and ultimately factor this polynomial. So I'm going to notice something for us about this polynomial. It kind of looks like something maybe you've seen in an algebra class. Maybe you took my algebra class last semester. That's great. So it kind of looks like a u squared plus 6u plus 9. It has that form. And because of that, I can look at that and say, oh, I know how this factors. That's u plus 3 squared. Well, this polynomial here is also a nice perfect square. So I can rewrite that one as p of x equals x squared plus 3 times x squared plus 3, like that. And I want to know where this actually equals 0. Now, it might be more convenient to write it as x squared plus 3 squared, and that's fine too. We need to find out where x squared plus 3 equals 0. So let's do that. So solve x squared plus 3 equals 0. Well, it's going to mean x squared equals negative 3, or x equals plus or minus the square root of negative 3. Now, sometimes when people do this, there's a little wishful thinking that happens. And as people wish that negative wasn't underneath the square root. It is. Sorry. So what can we do about that negative underneath the square root? Well, I can factor it this way. I can write that as square root of 3 times square root of negative 1. What happens to the square root of negative 1? It becomes I. So plus or minus square root of 3 times I. Now, that's formally the way to write this, but I like to be a little more informal on this one because sometimes people get a little sloppy here and write square root of 3i, and that's much different. And that would actually be the wrong answer here. And it leaves me in kind of a hard spot when I see people do that on an exam because it means something different. So I encourage you to write it like this, put the I out here. That way it's clear it's not under the radical. So it's just kind of being safer for you. So, yay. Now, let's see about factoring this. And as far as the factors are concerned, well, we'll start out with the roots. We had a root at I times the square root of 3 and a root at negative I times the square root of 3. And I'll talk about that later, but one thing to notice is that these roots occur in conjugate pairs. Now, if this is a root, let's see what the corresponding factor is. So there's, if I move this to the other side, I would get x minus I times the square root of 3 equals 0, of course, but I'm just interested in the factor. So x minus I times the square root of 3 and x plus I times the square root of 3. And that's how I factor this term in here. That x squared plus 3 factors into x minus I square root of 3 and x plus I square root of 3. So p of x can be written as x squared plus 3 squared, but that itself can be written as x minus I times the square root of 3 and x plus I times the square root of 3, and that's still squared. Now, if you want to square each of these individually, that's fine too. I really don't have much of a preference on that. But this is probably how you would find your answer in a book or on WebAssign. Let's take a look at one last thing here. The multiplicity. How many times does I times the square root of 3 occur as a root? Twice, right? And then negative I times the square root of 3 also occurs as a root twice. If you add up the roots and their multiplicities, what do we get? 4. And why is 4 reassuring here? Why is that a reassuring total? Yeah, it matches the degree of our equation, right? We had degree equals 4 equation, and now you can see you've accounted for everything in the equation, because with the roots and their multiplicities, we have 4. So, yay. Doing good on that first one. Let me finish up by remarking that there's a little bit more than a coincidence here, that if you got the negative solution here, then you'd also have the positive solution as well. So minus I squared to 3 and plus I squared to 3. They occur in pairs. And that's your imaginary zeros theorem. And basically it says if you have a polynomial with real coefficients and a plus bi is a root, then a minus bi is also going to be a root. So that's your complex zeros theorem. If p of x is a real polynomial, is a polynomial with real coefficients, and has a root at a plus bi, then a minus bi is also a root. Oops, my bad. And we're going to use that. We're going to use that idea to good effect. Not wasn't necessarily the next problem, but you know, some coming up. All right, the goal in this last one, problem number 14, was to write our polynomial in a completely factored form, and that was this down here. So are we okay with that one? Okay with 14? Let's look at problem number 16. P of x is x cubed minus 8. Now, this is a factorization that most people don't have a whole lot of love for. Does anyone remember even the name of it? Difference of cubes. Well done. Who was your intermediate algebra instructor? Oh, never mind. Yeah, I think it was me. Okay, me too. So difference of cubes. That's going to be a cubed minus b cubed. And we can also look at the sum of cubes. And the reason I want to write these down together is because there's some similarities. Now, with the difference or sum of cubes, you start out with what do you cube to get each of these? An a and a b. So you're going to have a binomial. But then that binomial is going to be multiplied by a trinomial. And the way to get that trinomial is to take these two terms, the a and the b, and square them. And that'll be the n terms of your binomial or your trinomial. But I need to do something else to get one more term, and that middle term is just going to be the product of those two things. So it's going to be a times b. So that's going to go in the middle. Some people want to put a 2 in there. There's no 2 in there. The last thing I want to remind you of is that I need to put in the signs. Brian, do you also remember that mnemonic I gave you guys about this? Soap. Yeah, well done. These two signs are the same. Opposite, always positive. See if you can't fill in this one down here using that same mnemonic. Same sign, opposite sign, always positive. All right, someone make me look good. What signs go in here? Plus, minus, plus. Thank you, Kim. All right, well done. Now, why do I care about that? Well, because this is going to factor just like that. It's going to factor as x minus 2. And then remember, as before, you want to take and square the n term, so it's going to be x squared and then 4. What's going to go in the middle? What term? 2x. And as before, same sign, opposite sign, always positive. So what sign should I be putting in here? Positive and positive. So that's P of x. Can you see one place where this graph's going to cross the x-axis? 2, right? I mean, that one's, you just read that off. But let's see if there's any other places where it crosses the x-axis, at least that I can see. Oops, wrong one. So, as far as where it crosses the x-axis, let's see. Well, let's just go up here. X cubed minus 8. Get rid of these. Yeah, I'm only seeing 1. That's right there at 2. What's that telling me about the other 2 roots of this polynomial? They're imaginary, right? Because this graph crosses the x-axis once, the other 2 times it crosses only in your imagination. So let's find those 2 imaginary roots. So to find the root of a polynomial, I want to know where this actually equals 0. And I can tell where this equals 0 with one of these, right? And we already figured that one out. X minus 2 equals 0 when x equals 2. But x squared plus 2x plus 4 equals 0, that's going to be a little bit tougher nut to crack. What do I have to do to find where that's 0? Yeah, quadratic formula. Ugh. All right, so test yourself. See if you can write down the quadratic formula. What is that thing? For solving ax squared plus bx plus c equals 0. What's the formula that we use there? I'll give you a second or two to see if you can remember it. Somebody got it? All right. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. How many people got that one? All right. So for my home audience, let the record show that everybody raised their hand enthusiastically. Got 100% on that one, so that's cool. Let's see if we can't fill this in. A, B, and C. 1, 2, and 4. Now this one's kind of friendly because all the values are positive, but especially if you have a value that's negative, I strongly encourage that you just write the quadratic formula with a bunch of empty parentheses and then fill it in with those appropriate coefficients. Now there's one thing I can kind of expect from working with this, and it's because I have 2 complex solutions that I'm looking forward to finding. That should be a 1 here. 2. Negative 2 plus or minus the square root of... This happens a lot. What did I do wrong here? It's negative 12. Why do we expect a negative underneath here? Yeah, because we expect imaginary numbers. We expect complex solutions. You're not going to get those imaginary solutions unless you have a negative underneath here. So if you're solving this and also, wait a minute, I'm getting real solutions, stop. There's a problem. We expected complex solutions. They come from right here. Let me split that up into 3 radicals. I like to put -1 as the middle radical. What can I put as these other 2? 4 and 3 respectively. Nice. So you put a perfect square out in front. Thanks, gentlemen. That's going to be 2i times the square root of 3 over 2. -1 plus or minus I times the square root of 3. Nice. So let's do the same kind of thing that we did just a moment ago, and that is figure out how this thing factors. So I've got roots and factors. We'll see if we can actually, well, let's see. No, all we have to do is have it factored, so that'll be good enough. So we'll start out with the friendly part. The root, we had a root at 2. We also had a root at -1 plus I times the square root of 3, and x equals -1 minus I times the square root of 3. Let's see what the corresponding factors are. Now, for the corresponding factors, I'm just going to move those terms to the other side. I'll get x minus 2 equals 0, but my factor is just going to be this. If I move these 2 terms to the other side, I'll get x plus 1 minus I times the square root of 3. How about down here? What's the factor that this is going to correspond to? Move that to the other side, it changes signs. X plus 1 plus I times the square root of 3. So our original polynomial is going to be the product of those 3 factors. So we'll call it P of x is going to be x minus 2 times x plus 1 minus I times the square root of 3, and x plus 1 plus I times the square root of 3. And there's our polynomial completely factored. And that's what you're looking for. As a bonus, let's note that the multiplicity here is 1 for all of these, but that again matches the degree. The degree of the polynomial is 3. Nice. How are you looking on that one? Okay. Again, notice you have complex conjugates for roots there. Pairs of roots like that. And we're going to use that in the next 2 problems. So, anything on problem 16 before I move on? You okay with those? Okay. Let's try and find the answer to problem number 38. So P is a polynomial, has degree 2, and roots at. Now, I'm kind of surprised that the book gave you both of them. It doesn't have to. If I tell you that x equals 1 plus I times the square root of 2 is a root. What's the other one have to be? What's the other root have to be? Yeah, minus I times the square root of, or 1 minus I times the square root of 2. So they occur in pairs. So, all right. But a lot of times on a test, what I'll do is I'll try and reverse engineer things. I'm like, okay, if I want these solutions, what polynomial should I give them? So let's do what we've done just a moment ago. We had x equals 1 plus I square root of 2, and x equals 1 minus I square root of 2. Let's take a look at the factors. What would be the factors that correspond to these roots? How did I find them just a minute ago? What did I do? Yeah, I set it equal to 0, right? I moved everything to the left-hand side. So if I move this to the left-hand side, what happens to the plus 1? Minus 1. What happens to the plus I times the square root of 2? Minus I squared root of 2. So we get that factor. I'm not worried about the equals 0 part. I'm worried about the factor. And that's this right here. And there's another factor as well. AC, what would that factor be, please? Perfect, thank you. So to find my polynomial, I want to multiply those two polynomials together. So P of x, give yourself a little room up here. P of x equals product of these two things. X minus 1 minus I times the square root of 2, and x minus 1 plus I times the square root of 2. Okay. Well, what's the old saying? Work harder, or work smarter, not harder, right? Let's work smarter. Let me put some parentheses in here. Because as it stands, if I had to multiply this out brute force, it'd be x times all three of these things. And then negative 1 times all three of these. I'd have 3 here and 3 here. I have a total of 9 multiplications and additions. Yeah. I don't see anyone like going, come on, Jeff, let's just multiply it out. All right. There's not a lot of eagerness in that regard. So let me do this. Let me put parentheses around that x minus 1 term. And just regard it as one thing. And then that one thing starts to look like maybe something kind of familiar. And that kind of familiar thing would be this. A minus b times a plus b. Let me make it a little bit less abstract. A minus b times a plus b. What happens when I multiply a minus b times a plus b? Do all the cancellation for me. What's the bottom line? A squared minus b squared. Oh. That's kind of what I got here. What's my a? X minus 1. So that is going to be x minus 1 squared minus b, which is I times the square root of 2 squared. Now these you're going to end up squaring out binomials so often that it's probably not a bad idea just to know how to do this in your head. I mean, you can get away with writing it as a minus, x minus 1 times x minus 1 and foiling it out. But let's see if we can't do it simpler. I know I'm going to end up squaring both of these. So I'll have an x squared and a minus 1 squared, which would be 1. The middle term, I always borrow this exponent here, just for visual. This times this times this. 2 times negative 1 is negative 1, or excuse me, negative 2. Negative 2x. So the middle term is negative 2x. Oh, okay. So again, work smarter, not harder. Now how about over here? Minus I squared. What's the square root of 2 squared? 2. Okay. Can anyone simplify this much for me? What happens there? Good. Minus I squared. Well, I squared is -1. Negative times a negative is positive. So overall, that equals a +2 there. The bottom line for my polynomial is x squared minus 2x plus 3. That's the answer I'll be looking for. We're okay on 38 there. There's a good little trick here, and we'll use it again in problem 42. We'll make problem 42 a little nicer, and I'll also show you a graphing calculator trick to check your answers. But reviewing things here, I got the roots. I turned those into factors. I multiplied the two factors together by realizing that, you know what, if I put parentheses around this, I can think of this as a minus b times a plus b. So this is my a, that's my b. A squared minus b squared worked out pretty nice. Let's try a different one. Problem 42. Problem 42 is probably a little bit closer to what I would put on an exam. I want a polynomial q of degree 3. And q is going to have a couple things going for it. Q is going to have a root at -3 and a root at x equals 1 plus I. But what's one thing missing here? Well, we'll figure that out as we go. Root, factor, multiplicity, so I had a root at -3, root at 1 plus I, Can someone help me with the factors? Algebra? What would the factors be corresponding to x equal -3? Good. X plus 3. You want to do this one too? Perfect. Now technically these both equal 0, but we're interested in the factors, so we'll just work on these part. But to get the factors, you're just moving this stuff to the left-hand side. So the multiplicity here would be a 1 and a 1. That only totals up to 2, and I know I need a degree 3 polynomial. So it's telling me I'm missing something. What am I missing? The conjugate, right? So there'd be this one. This is more like the kind of problem I'm going to give you on an exam. 1 minus I. So I get x minus 1 plus I equals 0. That has multiplicity 1. And now this matches. My multiplicities add up to 3, and my degree is 3. So we're in good shape. Let's find the polynomial, q of x overall. Q of x is going to be a product of these three factors. X plus 3, x minus 1, oops, bless you, x minus 1 minus I, and x minus 1 plus I. Now, as far as multiplying this out is concerned, I'd play a couple games. First of all, I would concentrate on this part first. Let's multiply those together first, and, clean up this imaginary stuff, and then I'll worry about distributing in the x plus 3. And within that context, let's play the same game we did the last time, and that is regard this as being of this form, where I've got a minus something and a plus something. Give yourself a second to see if you can't write down the next line. What am I going to get down here? Okay. You should have written down this. X minus 1 squared minus what else squared? I squared. All right. So the nice thing is that we just did the x minus 1 squared. We know what that is. So that's going to be x squared minus 2x plus 1 minus, what happens when I square I? What do I get? Negative 1. So overall, I'm left with x plus 3 times x squared minus 2x plus 2, like that. Now that you've cleaned up that complex part, we'll take care of the other part. But are you okay with our trick here? I think it saves a lot of writing, a lot of errors, to be honest. All right. Let's finish this up. I'm going to distribute. First, I'll distribute the x. So I'll distribute the x to all three terms there. And that's going to give me x cubed minus 2x squared plus 2x. And then I've also got to distribute the y. Or I mean not the y, but the 3 here. So it's going to be 3x squared minus 6x plus 6. If you notice, I wrote it kind of in a staggered manner. Why did I stagger it as I distributed? Yeah, like terms. Yeah. Perfect. So x cubed plus x squared minus 4x plus 6. Cool. So that's my problem, q of x. Now, this took us a little while to do. And you can imagine that, it's going to be worth more than 1 or 2 points on an exam. So maybe you want to check it. How could you check that this problem does exactly what we expected? There's a few ways. One or two of which I was hoping you'd know. Yeah, you can check the graph, right? So if you check the graph, and here's my polynomial. If I check the graph, what should I see? I should see the graph goes through the x-axis at what point? Negative 3. All right, so let's just set up my window like this. I don't know. These are just guesses. Take a look at the graph. Uh-oh, did I type it in wrong? Let's see. Oh, yeah. Oh, no, wait. Oh, yeah, it should be a plus 6 here. My bad. All right. There you go. But I didn't even really need to graph this in order to see that I got that part of it right. I could just go to the table. And if I type in a -3, then what should I get for the y value? 0. So that works. But let me show you another way, because that only works for real numbers. Actually, you know what? That's a good question. Let me see how I do this. 1 plus I. Yeah, it won't let me put in a complex number here. But I have two other roots that I'd like to check. So if you have a graphing calculator, follow me along with this. From the home screen. From the home screen, type in 1 plus I. Now, where do you find I? I you find down here at the bottom, right above the decimal point. Right? So 1 plus I. And before you hit the Enter key, let's store that. So you can store that by hitting the Store key right here. Store that in X. Now, X is right next to the alpha key. I'll store it in X. So great, I've got this stored. Wonderful. Now, how do I work it from there? Well, I want to type in the polynomial. And let's see if my solution for X actually works. If I take X raised to the third power plus X squared minus 4X plus 6, hey, I got 0. That's what I should get. Now, does that happen for every value of X? No. If I take X equals, say, 5 and store it in X, and I choose and type that expression again, I don't get 0. But what if I stored -3 in X? What should happen when I type this expression with -3 for X? Should get 0. Beautiful. So you can actually check all of your answers in this. The only ones that are going to give you 0 are the ones that we created. These 3 right here. Cool. So we nailed that one. Okay. How are we looking on that one? All right. Let's do a couple more here. Problem number 50. Problem number 50, we're going to put this together kind of like what you might see on an exam. Y equals 2x cubed plus 7x plus 18x plus 18. And we're going to start by working with the rational root theorem. So I need P and Q. Well, P and Q come from factors of a couple of these numbers, right? P is going to be factors of 18. Thank you. It's going to be a squared. Yes. Yeah, because otherwise it was collapsing to be a 25x. Thank you. What are the factors of 18? 2, 3, 9, and 18. And then how about Q? What are the factors that, or what am I going to look at to factor and get Q? 2. So that's an even shorter list, a mercifully short list. So it's going to be 1 and 2. Now overall, my possible rational roots. Possible rational roots have to have the form plus or minus P over Q. And if you forget the plus or minus, you're kind of putting me in a tough spot. Because, I mean, you need both of them. In particular, I think we need one for this one. So we get plus or minus, well, 1 over 1. And then 1 over 2. Then 2 over 1. And 2 over 2. 3 over 1. And 3 over 2. And this is starting to get kind of boring. 6 over 1, 6 over 2, 9 over 1, 9 over 2, 18 over 1, and 18 over 2. No, you don't have to put over 1. I'm just doing that so that I can show you that I'm being methodical. And that way I don't leave out anything. Now that I've been methodical, let's try and get rid of some extra garbage, right? For instance, I don't need 2 over 2, right? I already got that here. That's 1. I can also get rid of 6 over 2 and 18 over 2, right? So a lot of these are kind of redundant. So we don't have to list the redundancies. It does help me if you list overall, you know, what are the possibilities that are left. Bonus points if you list them in ascending order. So plus or minus, please don't forget the plus or minus. It'd be 1/2, and then 1, and then 3/2, and then 2. Then what else? 9/2, 4.5, 9/2, and then I missed 3. Darn it. 3, and then 6, and then 9, and then 18. So wow, we got what? 1, 2, 3, 4, 5, 6, 7, 8, 9. Just FYI, appealing to my inner math nerd, there are 362,880 different ways you could arrange these 9 numbers. You only have to list one of them, okay? I'll make that easy for you. Just list one of them. Bonus points if you can list them in the increasing order. It makes it a little easier for me to decipher your answer. All right, but which one of these should we check? Which one of these do you think is going to actually be a solution to this one? I mean, if I was going to guess, what do you think a good place to start would be? What should I do? Graph it. Thank you. I really appreciate that. Graph it. So we'll take a look at problem number 50, and we graph it, and bam! Winner, winner, chicken dinner, right? So looks like negative 1.5. What would that be as a fraction? Negative 3 over 2. And good for us, negative 3 over 2 was on our list of possible rational roots. So we'll start out there. Negative 3 over 2. Just a reminder, our polynomial is y equals 2x cubed plus 7x squared plus 18x plus 18. And negative 3 over 2 is a root. Let's put that in here. 2, 7, 18, and 18 again. Now underneath the 2, to start things out, what should I put? 0. Put that 0 there. It's add to go down, multiply to go up. Now some of you might not be really happy about multiplying by negative 3/2. You're like, oh, terrible about that. And you know what? I've got a quick fix for that. That quick fix for that is to store it. So take negative 3 divided by 2, store it in x. And now when you need to kind of go up here and you're like, oh, I'm not really a big fan of that, just multiply. Type in 2x. Oh, yeah, -3. I knew that. So we get a -3 here. Add going down gives me 4. And then, oh, man, 4 times -3/2. Hey, no problem. 4x gives you -6. That gives me a 12. Is this idea working for you guys? Do you like this one with the x? All right. So, Kennedy, what do I get up here? -18 for a goose egg here. Perfect. Thank you. So, what does that tell me? It tells me my original polynomial y can be factored into x plus 3/2 times something else. Sarah, what's that something else? What's this? Perfect. So these are the coefficients of my polynomial. 2x squared plus 4x plus 12. Now, thank you, Sarah. Eventually, I want to solve where this equals 0. And, you know, at the moment, it's kind of a pain. But do you notice anything about this polynomial here? Like maybe a greatest common factor? 2, which is behind x squared plus 2x plus 6 there. What do you think? For convenience, you want to take that 2 and just distribute it into here? Yeah. Yeah. I knew that's what you were dying to do. So let's take care of that. But let's look back at the graph. We had one real solution. Are we going to get any more real solutions? What do you think? I'm thinking that's it. We got one real solution, so that leaves me what down here? Complex solutions. So to find the remaining solutions, if I want to know where that equals 0, I know where this equals 0, I've got to use the quadratic formula here. And you expect a couple complex solutions on that. Let's see that problem doesn't disappoint us in that regard. X squared plus 2x plus 6 equals 0. Plug that into the quadratic formula. X equals -2 plus or minus the square root of 2 squared minus 4 times a, which is 1 times 6 over 2 times 1. 4 minus 24 is -20. There's where your negative numbers or complex numbers are coming from, is right there. Let's split up -20 into 3 roots. What would they be? Perfect. 4, -1, and 5. -2 plus or minus 2i square roots of 5. Don't just cancel this 2 and this 2 or this one and this one. Factor out that 2 from the entire numerator. -1 plus or minus I times the square root of 5. I can now cancel those 2's, and I'm left with -1 plus or minus I times the square root of 5. You guys are making me nervous. What is it? All right. Yeah. All right. All right. Yeah. All right. I guess because I have kids, I ignore some of those things. Yeah. Okay. So Overall, if I wanted to, I could write that polynomial as a product of factors. Let me do that just for the practice. Not that I think that the problem requires it. I think they're asking you just for the solutions there. Is that right? Let's take a quick look here. Problem number 50. Yes, find all the zeros. So technically we're done, but just for the practice, let's go back and factor that. So one of our factors was 2x plus 3. The other ones come from this term and these binomials. So we'll see, we have x equals -1 plus I square roots of 5, and x equals -1 minus I times the square root of 5. If I turn these into factors, it'd be x plus 1 minus I square roots of 5, and x plus 1 plus I times the square root of 5. Overall, my original problem can be written like this: 2x plus 3, x plus 1 minus I times the square root of 5, and x plus 1 plus I times the square root of 5. But there it is, completely factored. Not that the problem asked for it, but it's just good practice because you got an exam on Wednesday. I know I said Thursday. I said Thursday in the email. If y'all want to come in early on Thursday morning, I'll be here at 8:30. Take that. All right. We're looking okay with problem number 50. Okay, let's do one more kind of like that. Actually, very much like that, and that'll finish things up for us from section 3.5. It's problem number 56. So y is x to the 4th minus 2x cubed minus 2x squared minus 2x minus 3. Since it's so mercifully short, let's practice rational root theorem with this one. P is going to be the factors of what number? Coop? All right, so the factors of 3 are what? 1 and 3. Cool. And Q is the factors of someone else? Just 1, right? So, like I said, that gives us a mercifully small list of factors. So, plus or minus P over Q, 1 over 1 or 3 over 1. And please put that plus or minus out in front. Overall, if, it's not a guaranteed if, but if this polynomial has some real roots, then it's going to be crossing the x-axis at either -3, -1, 1, or 3. Now that's if it has real roots or rational roots. Or actually the rational roots is this is where it has to cross. So let's see where it actually does cross. Now before I do, there's a couple end behaviors of this graph that are possible. There's this one, this one, this one, or this one, A, B, C, or D. Which one of those end behaviors do we expect? C. You expect something that points up in both directions. Let's see that we're not disappointed. Here, and 56. Yeah, pretty much like what we expected. And as a bonus, I think we can see the two roots. There's one at -1 and another one at 3. So let's work with those real roots and see what progress we can make with our polynomial. So the roots were starting at, well, we'll work with the one at 3. So from the graph, x equals -1, x equals 3. Those are the roots. And we can factor them out with synthetic division. So it's going to be a 3 here. 1, -2, -2, -2, -2 again, and finally +3. What do I put underneath that 1 to start with? 0. Want to have that 0 there just so that you don't get turned around and put something else funky there. Did I put in an extra 2 there? Hate when that happens. All right. Here. There's a better way I can fix this. Sorry about that. All right, so let's see. Let's try it again. We've got 3, 1, -2, -2, -2, and -3. Is that better? And then we got the -3 there. So, as I was mentioning, we'll put a 0 underneath that 1. Just kind of a little placeholder to get us going. And then from there, it's just add, multiply, 3. It's going to be a 1, then a 3. 1, 3, 1, 3, 1, 3, 0. Beautiful. Now what's that telling me? It's telling me that my graph, my polynomial, can be written as x minus 3 times something else. I think someone up front's got me here. What is that? That's your constant term, x squared, x cubed. So x cubed plus x squared plus x plus 1. And now you got to keep going. We also know that x equals -1 is a factor. There is actually a clever way that you can keep going. There's nothing wrong with it at all. Well, we are going to work with a new polynomial, but you know what? I'll go back to this in a second. For now, we're going to take the new polynomial. Our other root was at x equals -1, right? So let's put -1 out in front here. 1, 1, 1, 1. Our little starter 0. -1, -1, 0, 0, 1, -1, 0. Beautiful. That enables me to rewrite this as x minus 3 times x plus 1 times something else. What else is left? X squared plus 1. Now, a minute ago, I was saying, oh, well, there's another way you can do this. And that other way you could have done it had you seen it, and it's not something that might jump out at you. But you could have factored by grouping. Remember that? If you have 4 terms, what will come out of here? X squared times x plus 1. What comes out of here? Just a placeholder of a plus 1. Plus 1 like that. These 2 terms match, so then you can factor out the x plus 1, and it leaves behind x squared plus 1. So it's a different way you can get this thing to factor. But hey, that's great. Now you can see where there's two complex solutions coming in here. I know that if I had to solve for this equals 0, x squared equals -1 gives me two solutions at plus or minus I. So to finish this off, remember if this is your root, if I have a root at x equal I, x equal -I, then they're going to form factors like this, x minus I and x plus I. X minus I times x plus I. So I've got all my roots. And then, of course, I got all my factors. But the roots is what the problem is looking for, right here. All right, for homework, try 7 through 33, 37 through 41, 47, and 49.